So today's paper is about avoiding inference heuristics in few-shot prompt-based fine-tuning. So this paper focuses mainly on sentence pair classification task, and what they found is that prompt-based fine-tuned models they don't perform very well on these kind of tasks, and the why and the reason is, for example, there are two sentences x1 x2 and they have a lot of overlap in terms of words, but they don't mean the same, or they don't entail each other, or they are not duplicates of each other. But the tendency of the model is to predict that they are duplicates or they entail each other. So so in this paper, they study this behavior, and also a way to minimize this error using regularization. So, and also what they found is that this behavior is less present in zero-shot evaluation of the prompt-based models, and is more present when you fine-tune it. So fine-tuning actually is being destructive for this kind of task. So they have two kind of comparison. So one is for prompt-based fine-tuning. So in prompt-based fine-tuning, they convert the task, the sentence pair classification task, into a masked language modeling task. So this is CLS token, this is SEP token, and this is S1 is the sentence 1, question mark, mask, and S2. So for the first, so there are two approaches. One is called classifier head, and the other is prompt-based approach. So in the classifier head, they simply have two sentences separated by a CLS token, and the output of this is fed into the classifier head, which is used further. For prompt-based approach, they convert in this format, and they use masked language modeling to get the result. So, and the dataset which they are using is 3 English datasets from GLUE, MNLI, SNLI, and QQP, and the model they are using is Roberta Large. So this is one of the main figure of this paper. So here, this is the input, and after the prompts are added, it becomes into, for example, some function of x. That's the prompt, and it is the Roberta Large is fine-tuned on this data set, and you get the predictions. So if you see here, these are a number of training examples. So this is zero shot, no examples used, and you slowly increase the number of training examples. So in this case, the more examples we have, the better the performance is, right? Now every dataset like QQP, SNLI, and MNLI, they have another dataset going along with it. This is the challenged data. This is more challenging. So every dataset has a more challenging version. In MNLI, there are 3 more versions. So in these challenged datasets, the examples exhibits word overlap between the 2 input sentences, but are labeled as non-entailment for NLI and non-duplicate for QQP. So they have more sentences where the sentences are overlapping, but they are labeled as either non-duplicates or non-entailment. So that becomes a challenging dataset for these models, and they performs very, very badly on this. So for zero shot is this much, and the more examples we have, the performance degrades. And the other interesting thing is to see, and it happens for all the datasets, here. Now the other interesting thing is to see which kind of examples they perform badly. So here it is duplicates and non-duplicates. So for duplicates, for example, if there are two sentences having a lot of word overlap, but the model is going to predict as duplicates, so it's like more. But the moment the sentences are non-duplicates, it's going to perform very, very bad. So it's not, the model is not able to identify maybe the subtle word differences when the meaning itself changes. So it's not able to detect that in all of the three cases. Like here it is non-entailment, it's decreasing. So to mitigate this problem, they introduced a regularization term along with this is the standard cross entropy loss, and we have regularization term for this, and then they compare it so that these are the results. So zero shot is there is no this is just the zero shot, like Robert a large zero shot. This is fine tuning the entire model. This is with the regularization term, and this is when they fix 18 layers, first 18 layers of Roberta large and fine tune the rest. This is fixing 12 layers and this is fixing 6 layers. Classifier head is for this prompt based, the input was converted into a mask language modeling. For classifier head, we directly input the output of the CLS to the classifier head, which we discussed here. So in this table, we can see that even so, when we fine tune, we have a very good performance, 84. And when we put the regularization, so this is in distribution is you train the model on MNLI and you test it on the same dataset. This is when you train the model on MNLI and test it on hands. This is the challenging dataset. So we want it to perform better on this one too. Not we want it to perform better on both of these things. So that's why they have this average performance. So in zero shot, it was like this. In fine tuning, this improved, but this decreased. So this is the overall average performance. And with regularization, this is relatively better. And this one is also relatively better than just fine tuning. So it prevents the damage which the fine tuning was doing. So this is better. This has been seen in all the three datasets. And they tried fixing this thing, the layers, but there is no, not much pattern over what's going on here. So I think that's the main. So I think this is the kind of main point of this paper, is that there is a way we can fix this, but this kind of behavior is present in this particular task. So yeah, for more details, you can read the paper. Thank you.